Now we'll discuss some specific techniques of integration. In this video, we're going to look at U-substitution. So to start off with, I want to remind you of the chain rule for differentiation. The chain rule deals with composite functions. If we want to differentiate f of g of x, then we get f prime of g of x multiplied by g prime of x. So in order to connect this to U-substitution and integration in general, first of all, what we can do is take that rule that I have there and integrate both sides. So starting with the chain rule here, that means that the integral of the left side with respect to x should equal the integral of the right side with respect to x. And looking at these two sides that I have here, it's the left-hand side that can be simplified quite nicely. So notice we have on the left here the antiderivative of the derivative of a function. So we know now at this point that the antiderivative of the derivative of f of g of x should simply be f of g of x. So rewriting the right-hand side exactly as we have it, what we get out of this is, with regards to integrating, if I see something that can be recognized to be of the form of what I have on the right, this gives us a nice way to find the antiderivative. So specifically, the method here is that you're going to imagine that you're going to try to integrate something of the form f prime of g of x, g prime of x. So the name U-substitution comes from the idea that what we want to do is change this to an integral involving a new variable u. So to be clear, u is a function of x, but often notation-wise, instead of writing u of x, we just write u. So when I'm looking at this, the key thing, and we're going to get a lot of practice with trying to find a suitable u, is that I see here that this composite function has the inside function being g of x, and then the other thing that's very important here is if that is u, its derivative is also present here. We're going to see that that's going to be something we want to happen. So when I'm using U-substitution, I typically pause, identify the function that I'm going to call u, and like I said, technically this is u of x, but I'm just writing u. And then once I write down what u is, I want to make sure that I can relate likewise what the differential or the derivative of u is with respect to x. So in that case, once I've done that, we're able to rewrite the integral that we started with in terms of the new variable u. So f prime of g of x now becomes f prime of u, and g prime of x dx now becomes du. And the nice thing about this is, again, I have this simplified form where we're looking for the antiderivative of a derivative. So we know we're going to get out just f of u, and of course if it's an indefinite integral, we would put a plus c. And something that's very important here is that the original integral was expressed in terms of variable x, so you want to end up with your answer written in terms of x as well. So we know that u is g of x, so that allows me to say that my answer is f of g of x plus c. So we're going to use this technique quite a bit throughout the course. And like I said, if it is new to you, then the idea is that the more practice we get, the better. And so in our class in particular, we're going to see a lot of examples of going through this technique. And it's going to be important to not only be able to decide the best choice for you, but also when we start to look at several techniques, being able to determine when it is that U-substitution is the technique that you want to apply. So for an example where it is a good technique here, what I want to do is use a U-substitution. So again, just to be clear, when you're looking at this integral, you're trying to envision it as being of this form. So when I look at it, I need to decide what u could equal. Well, what we saw above is that typically, if you notice a composite function, maybe choosing u to be the inside function would be a good choice. The other thing that I mentioned that's, well, actually, I wrote this down. This is not quite what I wanted. That actually would have been a much more complicated integral, which we can solve. But let's look at this. So what I had before, I was missing the x. So what I was going to say is that what's nice about this is the inside function, x squared, its derivative is present in here as well. So suppose that I have u, and I need to decide what it is. So let's choose the inside function, x squared. Then once I establish what u is, then I want to find du. And that's saying differentiate u with respect to x. Well, the derivative of x squared is going to be 2x dx. So what we can think of here is that, again, within this integral, here's u, and then this part's kind of separated here, but the 2x dx is du. So everything's accounted for in this. And I can say that the integral that I started with, the integral in terms of x, is now equivalent to the integral where I take sine of x squared becomes sine of u, and 2x dx becomes du. And now I've turned it into an integral where I just have to know the antiderivative of sine. I know that the antiderivative of sine is minus cosine. And as we mentioned before, it's going to be very important not to stop here and leave it in terms of u. If you look at this answer in the original integral, it's not clear what u has to do with that. So we want to then replace u with its definition, which was x squared. And this is my final answer. And of course, especially when we're just starting to practice with this, what's nice is that if you can check that if you take the derivative of what we have boxed there, that you do in fact end up with the integrand. So one last thing I want to mention in this video is that we have to be a little bit careful with definite integrals. So the example I did above, there were no bounds on that integral. The process is pretty much like we outlined there. The reason that definite integrals need a little bit more care is that when you have bounds on an integral, those bounds pertain to the integration variable. And what we're doing in this process is we're changing the integration variable from say x to u. And so we need to be clear about what the bounds are in terms of x and what they are in terms of u. So there's really two ways that we can deal with this. So let's look at the same integrand that we just looked at, and we'll put bounds on here. So to be clear, if I were starting this problem from scratch, I would go through exactly what we did above, the same U-substitution, but I'm going to take advantage of the fact that we already did that work. So in terms of approaching this, I'm going to go through two methods. You can use either, but what I want to specify is that I often think there's something a little bit more simplistic with I'll do the first method. So the first method here is to change bounds to be in terms of u. So when I make my substitution, u equals x squared, then what we can do is say that knowing that x is equal to 2, which was the lower limit of integration on the example, that implies that u is 2 squared or 4. And knowing that x is 3, the upper limit of integration, that corresponds to u equaling 3 squared or 9. So once you make your u substitution, when you're rewriting the integral, in terms of the new variable, you put the new numerical bounds on there. So when I write this as sine of u du, then I want to indicate that the bounds here, in terms of the new integration variable, are 4 and 9. So we can anti-differentiate. We already said that we would get minus cosine of u. And the nice thing about this is that unlike my example, I don't have to now rewrite it as minus cosine of x squared because I've changed the entire problem to be in terms of the new variable. And plugging these in, we would get minus cosine of 9 minus a negative, or plus cosine of 4. So this is one method, and like I said, this is my personal kind of preferred method. But to be clear, another way we could go about this is to change antiderivative back to x. So hopefully this will gain some clarity in a moment here. So suppose that we're doing this and I'm using my U-substitution. If I don't change my bounds to reflect the new variable, well, first of all, I should be very clear about that. Now, typically, if you're writing numbers on the integral here, the assumption is going to be that they correspond to the integration variable, which would be u. So I can kind of indicate, and it's almost a reminder to yourself as well, that these numbers I'm putting here correspond to the original variable. So when you anti-differentiate, then instead of having changed these bounds to be in terms of u, we change my antiderivative back to the original variable. And now we can plug in those original x bounds. And notice, importantly, we get the exact same answer that we got above. And so this is a suitable approach as well. The reason I personally kind of prefer the first method is we're going to see some more kind of symbolic examples where maybe you don't actually need or know the specific antiderivative for an example. And in that case, I think it's a little bit cleaner to use the first method. However, both of these are fine, and I'll point out that the important thing that you should note here is that regardless of which of these methods we use, there has to be a point in which you reconcile the distinction between variable x and variable u. And the common mistake here, I would say, is for somebody to change it into u and mistakenly apply the variables, the bounds from the original variable x. So just be careful with that. And like I said, we'll have more practice with this as well. The other techniques we see, we won't have a similar issue with definite integrals causing particular problems, but it's always good just to be a little bit cautious with that.